Hello, this video is on prime numbers and prime factorization. We talked a little bit about prime numbers and composite numbers a couple days ago, but we're going to keep talking about this some more. A factor is a number that multiplies with another number in a multiplication problem. So for instance, if I write 2 times 3 equals 6, 2 and 3 are factors of 6. Another way to say that is a factor is a whole number that divides a number with a remainder of 0. So for instance, 6 divided by 3 gives you 2, so 3 is a factor. Or 6 divided by 2 is 3, so 2 is a factor. Okay. A good example from the book about when factors might be useful is, let's say an instructor plans a dance routine for 20 dancers in rows, and each row needs to have the same number of dancers. What are the arrangements the instructor can use? So if the instructor has 20 dancers, we can get rid of this 2 times 3 part now, and we want to know how they can be organized. Well, you could have one row of 20 dancers, because 1 times 20 is 20. You could have 2 rows of 10 dancers each. You can't have 3 rows because that would be an uneven amount. Excuse me. But you could have 4 rows with 5 dancers. And you can do the opposite of that. So you could have 5 rows of 4, 10 rows of 2, 20 rows of 1, which would kind of look the same, right? So these are factors. So if a problem asks you to list all factors of 20, some people might do this using the rainbow method. So 1 times 20, 2 times 10, 4 times 5. So those are all the factors of 20. Remember, a composite number has more factors than just one in itself. So for instance, 6, its factors are 1, 6, right? 1 times 6, 2, and 3. Right? So all those are factors of 6. So that is composite, right? Whereas a number like 2, its only factors are 1 and 2, right? 1 times 2. So this would be called prime. Some other prime numbers include 3, 5, 7, 11, 13, 17, 19. They kind of go on forever, but prime numbers can only be divided by 1 and themselves. So let's do a couple examples of prime or composite. So we'll call it prime or composite. Excuse me. So if the number is 51, well, using the divisibility rule of 3, we know that 5 plus 1 is 6, which is divisible by 3. So since this is divisible by 3, we know it is composite. Because 51 divided by 3, I think, is like 17 or something, right? 51 divided by 3, 34 equals 17. 47. I'm not sure about 47. So 2 is not, it's not divisible by 2 or 3 or 5 or 7 or 11 or 13 or 17 or 19. Another prime number would be 23. Yeah, so I think that's prime. 63, again, like 51, is divisible by 3, so that's composite. Now, some questions will ask, what is the prime factorization of a number? So, for instance, the prime factorization of 27. When you're finding a prime factorization, a lot of people use a factor tree, and it looks like this. So what times what equals 27? So 9 times 3 and then keep going until all the numbers at the bottom of the tree are prime. Notice what I did here is I brought down the number that was already prime. Every level of your factor tree should multiply to get that top number. So 9 times 3 is 27, 3 times 3 times 3 is 27. The reason I will force you to bring down these numbers is because in very big factor trees, like let's try, let's see, for 128, let's do. If we're doing 128 and we're making this factor tree, and we get 32 times 2 and 16 times 2 and 8 times 2 and 4 times 2 and 2 times 2. A lot of students, because of their handwriting and organization, will, when they list all the factors at the end, like 2 times 2 times 2 times 2 times 2 times 2, they'll often leave one of these out on accident. But by bringing it down every time, sorry, there should be dots in between all these to show that this is multiplication. By bringing it down every time, you're not going to lose any factors. Okay? So make sure you are bringing them down every time, because I don't want you to forget any of the factors. Okay, let's do one more example. So the prime factorization of 400, let's try. Prime factorization, remember we need to get all prime numbers being multiplied together. Every level has to multiply to get to that number. I could do 4 times 100. I could do 2 times 2 here. And everyone's tree could be different, but you should always get to the same answer eventually. But making the tree can be different, right? Alright, so that should be the final answer. I'll show you another way we could have done it, just to show you that it can be done in different ways. We could have done 200 and 2. We could have done 50 and 4 here. We could have done 5 and 10 here. 2 and 2 here. And then another 2 and a 5. 2, 2, 2. Either way, we should end up with 4 2s. And 2 5s. Over here we have 4 2s also, and 2 5s. You could also write these using exponents, so you could write this like this. Notice they are the same. But that is how you make a factor tree. Again, the journey could be different, but the final result should be the same. And that's it for tonight's video. Thank you.